forgot to start recording. Okay, so that was number 17, and we looked at this formula, and we rearranged it to solve for the number of moles, and we converted the volume to liters. When you made soap, you used 12 grams of sodium hydroxide, and you put that in 27 milliliters of water. So what was the molarity of that solution? This is the question. What concentration of sodium hydroxide solution were you dealing with? Well, where do we start here? Because we're not given a number of moles. So what we're after is the molarity, which is equal to, and I'll use the appropriate abbreviations, number of moles. So I'm going to just note that this is in moles, and this has to be in liters. Molarity is equal to number of moles divided by the volume in liters. Do we have the number, and we want molarity, so we don't have to rearrange anything. Do we have the number of moles? No. So that's our first step, is we have to convert that 12 grams of sodium hydroxide to moles of sodium hydroxide. So looking at that, we only have 0.3 moles of sodium hydroxide, so we might think, oh, this is not very concentrated. But remember, you had a very tiny volume of water. So we have to get our volume into liters. We'll do that. Okay, so we got 0.027 liters of H2O. Now we're ready to plug everything in and figure out what the molarity of that solution was. So moles divided by 0.027 liter. Your raw number for concentration. Yeah, 11.11111. So we have, what, 3 sig figs, so that would be 11.1 molar sodium hydroxide. I gotta tell you, kids, that's some potent stuff. That's some potent stuff. I mean, we're very accustomed to dealing with, 1 molar, half molar, nice dilute solutions. That is a very concentrated solution. So, hence all the precautions we took when you were dealing with sodium hydroxide solutions, because that's some pretty fiercely concentrated stuff. Okay, where are you at from a scale of 0 to 5? Gesundheit. So, if I've got some solution on hand, well, actually, let's go through the real calculations that I went through when I had to adjust the lab where you made hydrogen gas using magnesium wire or magnesium ribbon and hydrochloric acid. So here are the actual calculations I did. Okay, I've got hydrochloric acid, I've got magnesium, and I'm going to form hydrogen and magnesium chloride. Great, this is what I've got. This is the reaction we're going to run. Well, I need to know what volume of hydrochloric acid I'm going to need if we're using, remember I said we used to use 6 molar hydrochloric acid and we only had 0.1 molar. Is that 0.1 molar or 1 molar? I think it was 1 molar. We had 1 molar HCl. So here's the deal. What volume of hydrochloric acid will I need to fully react a 1 centimeter strip of ribbon? Oh, how do I do that? Well, I have to know how many moles of magnesium I need, and I have to know how many moles of hydrochloric acid I'm going to get in what volume of the dilute hydrochloric acid. So here's the thing. Here's what I can figure out. Let's look at what's the maximum amount of magnesium that I could react. Well, what's the maximum volume I've got in there? I need to have some water in there so that it doesn't start to bubble immediately so that you can do the whole layering thing. So let's say I want, okay, let's split the difference. The most hydrochloric acid I want in there is 25 milliliters. So if I've got 25 milliliters of 1 molar hydrochloric acid, how many moles of hydrochloric acid do I have to react, and then how much magnesium can I react? So basically, how long a piece of magnesium can I have you guys use? So here's the question. How many moles of magnesium can be reacted if we're using 30 milliliters of 1 molar HCl? So what do I have to do first? I need to figure out how many moles of HCl I'm talking about here. So I'm going to start out with molarity is equal to N over V. Remember, this is number of moles. This is the volume, and it has to be in liters. So I have volume and I have molarity. I'm solving for number of moles. So this is easy. Molarity times volume equals the number of moles I get. Now I'm using, I said 30 milliliters, so what do I need to do? I need to get it into liters, so I'm going to convert my volume. So V equals 30.0 milliliters. 1 milliliter is 10 to the negative third liters, so this is 0.030 liters for volume. Okay, and molarity is easy because it's 1 molar, so that couldn't be a whole lot easier. So 1 molar times 0.030 liters gives me my number of moles. Don't need a calculator for that one, do we? So we have 0.030 moles. Okay, now what I was really asking is how many moles of magnesium can I react? So now I know how many moles of hydrochloric acid are available in that. And I have to go back and figure out. Now when I did these calculations for your lab, what I did was I figured out what mass of magnesium I could react, and that's how, and then I looked at, basically I measured a couple chunks of magnesium ribbon to figure out, oh, okay, well 1 centimeter weighs about this much, and if I cut it down to a ½ centimeter, it weighs about this much. So, tell them to use 0.75 centimeters, and that's how I got those numbers. Okay, so how would we figure out how many moles of magnesium we can react? This is plain old Chapter 9 stoichiometry. GMA. Yep. So in this case, I'm going from moles of one substance to moles of another, so it's a one-step conversion. I have a lovely balanced chemical equation here. So 0.030 moles HCl for every 1 mole of HCl. For every 2 moles of HCl, I react. Pardon me, for every 2 moles of HCl I react. I can react 1 mole of magnesium. So 0.030 divided by 2, I can react 0.015 moles of magnesium. Tiny, tiny, tiny little numbers, which is why you were using like 3/4 of a centimeter of magnesium. But that's kind of how these calculations come out in real life. Do you want to do another one together? You want to do something where you're solving? Let's do something where you're solving for volume. Did we solve for volume yet? Okay, let's do that. Okay, so this is similar to the last problem, except I left off the whole balanced chemical equation and figuring out how many moles of something else. I left off the stoichiometry end. But if we have a reaction that we're running, and we know that we need 0.750 moles of sodium hydroxide, and all we've got in the lab is 0.10 molar sodium hydroxide, which is pretty dilute. The question is, how much of that do we need to get 3/4 of a mole of sodium hydroxide? So again, we're starting where we always start. Molarity is equal to number of moles divided by the volume. This is in moles. This is in liters. And we're given the number of moles. We're given the molarity. So how do we solve this one? This is one of the ones where I say this is the algebra solve that is most likely to be screwed up by all students across the board, top to bottom, sideways, upside down, If you struggle with solving for things in the denominator, your best bet is to go around the barn. So do all the steps. So mv equals n. Well, now it's easy to solve for volume because v equals n divided by the molarity, number of moles divided by molarity. Okay, so the volume of solution that you need is equal to 0.7 0.750 moles divided by 0.10 molar solution. What do you get? Okay, you get 7.5 liters. Hey, go ahead and add number 18 in the chapter review. We're going to do a quiz on molarity tomorrow. It'll be a FIP quiz, and we'll do some more work based on the results thereof, okay?
When are we going to do the package from?
If I didn't say it already, FIP quiz on molarity tomorrow. Homework probably due Monday.